Progress.
All right. So last time we were talking about chi-square test. We're going to talk about them a bit more today. Uh, I checked a couple different formulas that we can use in Excel. So we're going to play around with the Excel a little bit more as well. I tried to look up the formula for Fisher's exact test, and that requires quite a bit of programming. But there is something called a Yates correction, which is what I was actually thinking about when I was thinking about the Fisher's exact test. So we'll look at that. So with the chi-squared test, the formula that we deal with is just like we had before. And then I have to say like I equals 1 to n, and then put a whole bunch of i's on all of these things. The chi-squared correction that we're going to be using, it looks almost the same, except it deals with absolute values. And we add in this minus 1/2, then square that. And we divide that by e sub I. So this is essentially the same thing we were doing last time. Like at least up until that point. So that's what we did last time. Now we've got to make that little correction. That correction is there, again, if you have small numbers that are in some of these cell counts, you can get really weird stuff like we saw yesterday, where if I literally took or placed one more person in each of the other three groups, all of a sudden we go from, hey, there's something very statistically significant going on here to, no, there's not. So with this correction, that should help out quite a bit. And I will say with the chi-square test as well, we can use that to try to figure out what is, say, the appropriate distribution for data that we have. And I will say that that is going to be a question on the exam. So we'll go over it today. And depending on, again, how many samples we have, everything that we're looking at, we might even need to use chi-squared. We might even need to use the corrected version. All right, I'm going to call it Yates version. So let's see how those actually work out. So try to make this a little bit bigger so that all of us, everyone can see what I'm doing here. So I was playing around a little bit earlier and just seeing what type of awkward and weird stuff we can come up with. And then realized, oh, some of this is actually pretty cool. So just so we have some data in here, see if I have everything from last time. And more than likely I'm not, but who knows? Okay. Well, So I was saying last time that we can do a uh, two prop z test for proportions, or we can use the chi-squared. So let's go back to some data for Professor A and Professor B. With Professor A, let's say they had 100 students pass, and we'll say they had 50 students that did not pass. Professor B has 150 students that passed and 150 students that did not pass. So if we try, no, should say down here, total, so 150 and 300. So if everything goes well, we can, I'm just going to open up Minitab. Hopefully it'll let me log in immediately. And of course not. All right, now it will. So if we're going to try to see, is there a statistically significant difference between Professor A and Professor B? Again, we go to stat, basic stats, two proportions. We have to change this to say that our data is actually summarized data. For sample one, the number of events is 100 out of 150. Sample two is 150 out of 300. So options, just going to go with 95% confidence interval. Keep everything the way that we are, just standard stuff. So click on OK, click on OK. And then of course we get, this actually gives us a confidence interval for the difference between the two. But then we also get this p-value. And based on what we have here, the p-value for this is 0.001. So we've got this data. Now, if we go back to Excel, I'm going to fill this in as, say, 100, oops, and then 50, then 150, and 150. So what should our expected outcomes be here? We can either go in and use that column total versus row total and all that, or you can look at the data and say something like, say for this particular class, on average, half the students pass, or let, let's say 60% of the students pass, just so we have something here, okay? So for our expected value up here, we could come out and say equal to, since we expect there to be 60% of the total here, so 6.6 times, then I'm just going to say the sum of these two things. Reason for that is we can go back in, or if I do it like this, we can go back in, change values around as much as we want, and everything automatically updates. If I go in there and say, oh, the sum for these is 150 and just leave it like that, then we when we go to update things, we have to go back and change all these other values too. So from a programming point of view, trying to do it like this is a little bit harder at the beginning, but it gets us where we want to be. And then equal here equal to 0.4 times the sum of these two things. Then I'm just going to copy this and paste it. So hopefully, let me make this even bigger than that. So if I copy these and say paste them down here, but then I put a little parenthesis out in front, you can see what the formula is for these two things right here. And then what's the formula for these, oops, that should actually be 2 and a 3, then a 2 and a 3. All right. So if we want to calculate this chi-squared, again, if we want to use standard method, we say equal, open parentheses, observed minus expected, close parentheses, then square that, and divide that by the expected value. So I'm just going to fill in the rest of this. And then I'm going to have the total for this down here. Need to type in equal to the sum of those four things. So again, if you look, still trying to figure the chi-squared stuff out, that is the formula for it. Where it says total, and then 15.2778. I just typed in there equal to sum and then highlighted the four values that I want to combine. So once I've got that, I can even put in here chi-squared to beat. So this should be, based on the data that we have, this should be essentially a 2x2 table. So again, the degrees of freedom here are number of rows -1 times the number of columns -1. And these totals that we have here don't count for this. So 2 minus 1 times 2 minus 1, that's going to give me a 1. The confidence level that I am looking for, so if I want it to be 95%, I have to type it in as 0.95. And then I can look here and say equal to, then 1 minus, and then I'm going to use this chi-square distribution. And I'm going to use the total that I've got down here, comma, the degrees of freedom I have here, comma, then I have to say true. So when I was trying to do this yesterday, and I did chi-square dot dist and looked at the value, that's giving me essentially a percentage. And what percentage of the chi-square distribution has been covered by the value that we're looking at. 1 minus that actually gives us the p-value. So has everyone gotten this far so far? Okay. So I can hit enter. So that's telling me, based upon the data that I put in there and the expected outcome that I chose, the p-value for that is 0.00001. So it's really, really small. I can look here and say, I'll look up the chi-squared value to be. I can say equal to, and then just type in chi again. And there's this chi-square.inv, chi-squared inverse. That's my confidence level. And then my degrees of freedom, close parentheses. So that 3.84, that is the value of, if this total down here is greater than this value, we can come out and say there is a statistically significant difference that we found here. And in case anyone needs some help trying to figure out, like, is the p-value small enough? Should we reject, fail to reject? I can type in here, conclusion. And again, just so we can make this easier on ourselves, so we can change things up or put it in different values and not have to redo all the programming, I can say equal to if, and I can either do a comparison between the chi-square to beat and the total that's down here, or I can do a value or look at the p-value here versus the confidence level that we want. So I'm going to say if 1 minus whatever this value is greater than this. I believe I need to put the quotes in here. So what I'm doing here is if a 0.05 is greater than the p-value, that's telling us that there is a statistically significant difference here. So we should be able to type in something. If you want to use do that, you can do that. And then it's either single quotes or double quotes. I believe it's double quotes. So you can type in whatever you want. I'm just going to hit enter to make sure that this actually worked. Nice way to help you figure out what's actually going on here, right? And again, if you want to use something different, it's fine with me. If you want it to be more statistically rigorous, what would you say? The first thing would be we reject H naught. The second thing where instead of nah, dude, nah, you'd put in there, we fail to reject H naught. But I like what I got better. So has anyone here ever used an if statement before in Excel? Okay. So with all this, we've got all these different ways that we can try to do these different calculations. With the way that I have it right now, I'm assuming that there's a 60% of students pass. What happens if it's actually, say, 55? We can put a lot more like little things in here for you to calculate and play around with if we wanted to. I don't know that we need to, but let's say we did make a mistake and it's actually going to be 55%. I can now come back here, change that to 55%, change this one to 45%. Then again, come back here, 55%, come back here, 45%. And it's still telling me, dude, there's a difference. Now, if we wanted to use the Yates correction, how do we end up, or how do we do that one? Oops, wrong column. Looking at this, I need to take the absolute value of these two numbers. In order to do that, I have to type in ABS and absolute value of those two numbers. And then on the outside of that, say minus 0.5 and put in new parentheses. So once I've got that set up, I can hit enter. I'm just going to drag this down all the way. So again, if you're trying to figure out what that value or what I actually put in there, can check that out. Oops. Sorry, I'll try to make it even a little bigger than it is, just because we can fit it all on the screen. So put a lot of stuff in here. The degrees of freedom is a value that you're going to need to put in. So if we're looking at a column of data, so if I give you, so if we're looking at HR data and we're looking at how many, say, Black women are employed, white women are employed, Latino or Latina are employed, how many Black men, white men, Latinos are employed, that type of thing. So it's all going to be in one column. We're going to have to know how you calculate that degrees of freedom and put it in there. The confidence level that we want. is a value that we're going to have to put in there. And you're going to have to remember that you want it at, or that number has to be a decimal. So if we want the 99% confidence interval, you can't put in there 99. You have to put in there 0.99, okay? We could try to do something with Excel to make it so that no matter what you put in there, it would work. But I honestly don't remember how to do that. And anytime I did figure it out, I honestly stumbled upon it. So I'm gonna leave it as it is. But the nice thing about this is once we've got it done, I can come up here, change it to the 99% confidence interval. Still telling me that it's different. I want it the 99.9% confidence interval. To see how it changed over. So we can, the way that we've got everything set up right now, for this, I've got it set up for just four of these things. So if you need it in the future, if you need to do something like this with 10, 15, 20 different groups, which is actually possible to do. I don't know why you would want to do it like that, but it is something that I've seen come up quite often. Uh, you just take what we're doing here and you just expand it. So what were you just squinting at? Which part of it?
I got it.
Okay. So with something like this, you can easily put the values in that you think we should actually be getting. If we're going to be doing chi-squared, like I said, for, let's say, a distribution, a couple of the things that we need to know are what are the cutoff points going to be? So if I've got the normal distribution, or if let's say I'm assuming that I've got the normal distribution, I don't actually know. Value in the middle here is going to be mu. If I come forward, say one standard deviation, I come back one standard deviation. This right here, I believe it's about 34%. And then this right here, it's going to be about 34%. If I go from here out, say, two standard deviations, then go back two standard deviations, this is basically going to be 95% confidence level, which means that any area out here, it's going to be about 2.5%. Out here, it's going to be about 2.5%. And honestly, I don't remember what the value is that we can put in there, but we can actually calculate that. So we can use Excel to do this. We can use a graphing calculator to do it. We can use actually, I'll use the exam1 calculator to do this. So get rid of that. So if we're dealing with the normal distribution, average is 0, standard deviation is going to be 1. And I want to look at what is the value when we go from 1 standard or from 0 standard deviations out to 1 standard deviation. So that's the 34% that I just wrote down. If I change this 1 to 2, it's 13.6%. If I go 2 to 3 standard deviations, that's 2.1%. 3 to, say, infinity, that's going to be the percentage that we're going to be looking at. Do we need to go this far in depth with all that? Not really, or at least not usually. So you can see approximately what all these different values are. And if we're using statistical software, literally what it's going to do is it's going to look at the data that you put into it. It's going to find the mean, it's going to find the standard deviation, and it's going to find how many values are between, say, negative infinity and -2 standard deviations. And then the number that belong between -1 and -2 standard deviations, the number that belong between 0 and -1, 0 and +1, 1 and +2, 2 and positive infinity, and so on. Count the number in there. And then it's going to look at essentially how many should be in there, assuming we've got the normal distribution, okay? So let's say I've given you this data here, and let's say I tell you I have 100 samples, okay? I'm just going to call these A, B, C, D, E, and F. So based on this, how many should be in A? 2.5% of 100, so 2.5. A here is exactly the same as F, so this should also be 2.5. How many should be in B? 13.6% of 100, so 13.6. E is going to be the same amount. And then 34%, 34%. What's 34% of 100? 34. So we can actually figure out, again, assuming I've got 100 of these, how many belong in each one of those categorical groups. If you look here and you look up here, because in this case we've got less than 10 for our values in the for our expected values in these cells, we want to use that Yates correction, or we want to use a Fisher's exact test. If we don't, we get into the issues that we had last time. But one of the things we can do here is once we've got this data, we can compare that. This is going to be our expected values. We can look at what our observed values are, and we can go in and actually calculate the chi-squared value. When we're trying to figure out what is the best distribution for the data, it's not about finding a statistically significant difference or not. It's about finding one where the chi-squared value is the smallest. So when we're looking at these, it's not about getting it perfect. It's about getting the best approximation for the data that we can. We're never going to know what the exact true distribution is. The best we can do is try to relate it back to something that we are more familiar with and then deal with it from there. Which means everything that you did in your 301 class, everything that we do in here, it's not about getting the right answer. It's about getting the best answer that you can. It's about trying to be as close to true as you can. So of course, if let's say I've got 300 data points, well, 2.5% of the 300 are going to go in A, same value in F. 13.6 of 300 will go in B and E. 34% of 300 will go in C and D. Those are just calculations that you're going to have to make. So not too difficult a calculation, right? So long as I give you the percentages that you need to put in there. So if you wanted to try and say automate that. So if we want to use Excel, so I'm just going to come out here and say n equals, and then we're going to put in, I'm just going to make it 100 for here. And we'll look at cell 1, 2, 3, 4, 5, 6. We can go however far we want. Percentage of the data that should be going here. So already set that 2.5% should go in. So again, I need to say 0.025. 0.136. I believe it's more like 0.341, then 0.341, 0.136, and 0.025. And then our expected counted data, see how close did I get to? So that should sum up to be 100. I got it to sum to 100.004. So that's kind of good enough here. This is just going to be equal to the number that I'm starting with here times whatever I have over here. Because I'm going to keep referencing back to this cell B1, I want to make sure to essentially lock it in. Putting the $ in front of the B makes it so this always, always, always checks the B column. Putting the $ in front of the 1 makes sure it always checks that first row. So by doing $B, $1, I'm always looking in the B column, row 1. So when I've done that, there's my 2.5. Click on that. I now have all the expected values that I need. Okay. For those of you that have taken a couple programming classes before, I'm sure you're looking at this and thinking, God, that's simplistic. Can we try doing that in Python or C++, Java, whatever? Yeah, you can. I'm not going to stop you. Or if you're an engineer, you might want to put it into MATLAB. Can you do that? Absolutely. But we're using Excel. So for those of you that aren't very experienced with the programming, I know that some of this is you're looking at it and going, wait, what? Really? Huh? So trying to go slow enough so that everyone can get the answers here. Like I said, if I now give you n equals, let's say 250 samples, everything just updated based upon making that one change up here. Oh, wait, it wasn't 250. It was actually 247 samples. My bad. Well, there you go. Okay. And now if we needed to, I could say these are the expected numbers of values I have in the 6 different areas of the normal distribution. So again, this is cell 1, cell 2, cell 3, 4, 5, 6, however you want to look at it. Now we can look at it and see how many of the actual values we have, what is our observed data. And when you're dealing with the observed data, remember the observed data has to be integer values. It either is in a range or it's not. It can't be like, say, borderline, right? So if I trying to break this down, so if I say 0 to 2.5, I can put the square brackets around that. Then if I put round brackets over here, say 2.5 to uh so 2.5 plus a 13.6, so 15, 16.1. And everyone remembers what the square brackets and round brackets mean, right? Totally. Square brackets means it can equal, round brackets means that it can approach. So if you have 2.5, 0, it's in here. If you have 2.5, 1, it's in this group. So there's like a definite cutoff point for all of these things. Then we can figure out the rest of them later. I'm not going to worry about it too much. Well, actually, up to here, it should end up being 50%, right? So, but anyway, we with the observed data, because we're dealing with counts, it has to fit into one of the groups that we're looking for. And again, when we're trying to figure out what is the best distribution for the data, it's not about getting uh, statistical significance or rejecting or failing to reject a null hypothesis. It's about getting the smallest chi-squared value. You're never going to have perfect. No matter how much data you collect, it's never all going to fall into place unless someone made it up. So you can have stuff that's close to any distribution that you're looking for, but it's never going to fall in there exactly. And we just looked at the normal distribution here based on all these things. If we wanted to, we could go back and look at, say, the binomial distribution, 0 to 10%, 10% to 20%, 20 to 30, 30 to 40, 40 to 50, all the way up to 100. We can make all these different cells. We could calculate the percent of the data we expect to be in each one of those cells. That would be based upon uh, the probability of an event occurring, as well as the number of trials that we're dealing with. Uh, I'm not going to worry about that, but that is something that we could do uh, later on, maybe in work someday. Might need to do something like that. Right now, I'm just trying to get you guys used, or getting you all used to using Excel to do some calculations. All right. So that's the big thought, the big plan that goes in here. So, uh, we've got our chi-squared thing. We've got the corrected chi-squared thing. And one of the things that you actually find is like the corrected chi-squared calculator that we have here. It's going to work really, really well when some of the values in your expected column are small. If they're all larger than 10 or 15, uh, using the traditional chi-squared is actually going to be a better practice. So how do you know when to use what? You literally have to look at what's in what numbers are you getting in the expected columns. And I'm going to say, I believe the textbooks usually say if it's under 5, I'm going to come out and say under 10 and perhaps even under 20, you might want to use a corrected value. But if you've got numbers like we have here, where everything in there is above 50, don't use the corrected one. All right. Does that make sense? All right. So, and again, we can go in, we can play around with all of these. If we knew what the expected values were that Minitab is using here for the normal approximation and Fisher's exact test, we could actually go in and put those expected values in here. More than likely, the expected values that they were going for on that. Oops. So again, if we've got so again with Professor A, we said that so we're looking at pass versus not. 100 pass, 50 do not. Total here is going to be 150. Professor B, 150, 150, 300. Total out here, 100 plus 150. So that's going to be 250. 50 plus 150, that's going to be 200. Add these up, we should get the same 450. So if we do our expected values out here, so Prof A, Professor B, pass, not, and these are going to be our expected values. What do we have in here? For this cell, 150 times 250 divided by 450. What are we going to have here? 150 times 200 divided by 450. What are we going to have here? 300 times 250 divided by 450. What are we going to have here? 300 times 200 divided by 450. So I'll try to zoom in a little bit. It'd be really nice if one, I could actually write better, and two, if this wasn't so grainy. But again, 150, 250, 150, 200, 300, 250, 300, 200. Calculate those out, stick them into our calculator, and then we can try and figure out, does there seem to be a statistically significant difference? And again, if we're trying to figure out what is the conclusion that we need to come up with, sometimes having something like that is actually a bit beneficial. Does that make it a lot easier? All you have to do is look at that and nah, all right. Fail to reject the null hypothesis. Dude, it's different. Reject the null hypothesis, which is what we're going for, right? So we can do these calculations over and over and over and over and over again if we really, really wanted to. Do we really, 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 really want to? It's probably going to be part of the job at some point, right? So does everyone, hopefully everyone has the calculator set up like this, right? All right.
Can you go back to cell B2?
This one?
Yeah.
Yeah, so this is with the corrected data. Oh. I'm writing down hopefully some form or formula that help you guys calculate this stuff out. Let's see. So did you get that? We're getting there?
Change anything pi square power.
No. Well, that is, sorry. You said B2. I clicked on that, sorry. But that's what we've got in there. What you need to worry about though is what are the observed and what goes into the chi-squared stuff. And then the p-value, that's kind of important there too. So I will put a parentheses out here so you can see everything that's in there. And then for the p-value, put a parentheses there. I need to make this a little bit smaller to fit it all. For those of you that already have all of this, two more things to do here. Calculate A, B, C, D, and E. Use that to calculate your expected values, and then go ahead and use your calculator to figure out, is there a statistically significant difference? And again, with this, the way that we're doing it is we have no expectation other than the data happened, okay? So make it a little bit easier.
I know. What is that? Yeah, I don't know. I'm guessing that is a.
So So I'm copying that table up here.
It's just a guess.
Hopefully everyone can see this. Like, can everyone see the table up here a little bit easier? All right. So I will minimize that. Yeah.
So the one. So how are you finding A and C?
What's the total?
Oh.
Add those together, A. Add those together, B. Add those together, D. Add those together, E. Add those together, you should get C. If you add those together, you should get the same value. It's a way of checking yourself. Again, this is if we have no expectation or have no theory or anything else to guide us, we use the calculations that I've got over there.
A times B divided by B. You're okay. Huh? Do you want to?
Well, you have to calculate those. And then you have to put it in your calculator. Is there a difference? This is pretty much one of the questions that's gonna be on the exam. So we've got like 15 more minutes to get through this, so let's make sure we get it right. And then when it comes exam time, you've got your own Excel sheet that can do this for you, okay? I'll make this a little bit bigger, just because the other one was a bit larger. Sure.
Oh, it's the exact same number.
Also, you are like doing it the way that I've got it. Okay, so those are the, so based on like all that. Now the expected, that's what you're calculating.
Yeah.
So,
But I noticed that they're the exact same numbers on my spreadsheet as the ones you have up there.
like I didn't have to change on that, yes. Because if I put my number, the correct numbers on there,
Yeah.
all of a sudden everyone has to use.
Oh, yeah, but that's what I'm saying. I put in the correct numbers, and it's the same as over there, so. It's an Excel file.
Because a lot of different reasons why it could be going up different. Well, the tax rate is based on the complex law. Value to change.
Well, I know this is gonna change this.
Yeah.
I don't know if this yet, but I'm saying.
Well, we have 1 degree of freedom of interest, that's why. Confidence level usually. The p value is calculated based on. What you have down there. So. When you put the right numbers. So you have to do this. Yeah.
That's realize they're using some money. Well, you do it by hand. Yeah.
Well, like I said, the expected values here. Those are probably the people's problems, so those are not correct. Once I put those correct numbers in, everything else is gonna come through. And right now, literally nothing out there is gonna work at all. Because this is technically not calculating anything. And the thing up there is technically not calculating anything. So I go back here, get rid of that. I come back here, get rid of that. I don't know what's supposed to be in here, but let's say 90, 60, 170, 130 or something like that. So I've got everything flipping around on that. And then if I come back and change this. So at the 99% confidence level, we're finding a significant difference. So
That's just.
yeah. Like I said, one of the places I used to teach at, the professor gave us all on the final exam a 6x6. So 6 cells that you add together, 6 cells across. You do these calculations 36 times with the calculator to get your expected value. Then you plug in all 36 values all the way across to do your chi-squared. And then by that time, the exam is over, you failed because you only got 1 problem out of 7. So this is much less lower, much lower stakes. Right? So
Just plug the stuff we find there.
yeah,
Excel and then write down if there's a difference.
I want the p-value.
Okay.
So what I want from all of you are the 5 values you calculated and then the p-value. All right. And honestly, I don't know what the p-value is, but I have a pretty good idea of what it should be.
I'm just.
So-
Because we just the absolute one.
Sure, it's a lot.
Yeah, yeah. So I think this one.
So. First things first. What goes in there? Next one.
There you go.
Right.
Wait, we do it. Okay. This is. That's the expected. 160 and then 230.
No, it's right.
So you don't just sign your calendar. I think. And then this is. Oh, it's. Yeah. Yeah. It is actually. That's the yeah. This one. Hey, we're just making numbers. You. Okay, so no. Yeah. You're basically. Yeah.
I have it right.
Yeah, but. Well, I didn't.
Type in these numbers on your site.
They already figured it out. Let's do the legal summary real quick, okay? I'll get to you in a second. I'll get to you in a second. So 120, 30, 160, and then 200. So what did you get for the expected values here?
Oh, you want these ones?
Yeah, most important thing is the p-value though. And that isn't a correct fit p-value. But let's use what you got here. So it's gonna be roughly 82 there. 67 there.
90s. And 162.
Should make that one 98 and then
It's like 67.
and then like 68. So. Since the group back there already figured it out. First thing is you have to change the values that are in the observed column. Then you put in the values you got for the expected. There shouldn't be zero for any of it. None of these should be expected value of 0.
So we have some weeks on the. Right, almost first. He's the only two right that in 200 that other things. All good environments, but there's still 13 of one. Oh, okay.
So.
Yeah, three.
For the expected value here. Oops. It's gonna be.
Yeah.
How many total people do I have here? 150 and 360. Get rid of this, 4 tonight.
Got it. It was like. Excuse me, sorry. I just want to make sure. Oh, yeah, sure. Yeah. Thank you. Have a good one, President. Wait, you're trying. No, I agree. I found a lot of different. What's your problem? Yeah. Okay.
Yeah, I haven't got a chance to look at that yet. Pretty much on any Wednesday, I get up at 5:30 in the morning. Either driving or teaching or trying not to pass out until about midnight, so. but I will take a look at that. I've got some time to do that today.
Okay, I appreciate it.
All right.
Thank you.
Yeah, so you got the expected values, and then you plug it into the p-value. So I don't know if these numbers are, or I put in rounded numbers for the expected value, and I'm not even sure if they're correct or not, but you've got the right idea, so we'll go with that.
Have a good week.
Yeah.
Good?
Yeah.
Okay.
So did you get your question answered?
Yes, yeah.
Okay.
And we were trying to figure out what the confidence level was. We didn't know if it was 99 or if it was 95. So
Well, and for this particular case, if you look at it, confidence level tells you only affects like these things. But the 8,000
Thank you, Professor.
is what it is. Okay.
thank you,
Yeah.
thank you.
Oh, no, I have work in like.
For the exam, what like topics should we be studying and looking at? And like, are you gonna post like a study guide or anything?
Well, we've got Tuesday to go through and review everything,
Uh-huh.
so we will review everything.
Is it online or at home? Is it like on the computers in person or?
Haven't figured that part out yet.
Okay.
It'll be a thing. Exam one will definitely be a thing. Right? I guarantee it will. It'll be. It will exist.
A good thing, right?
Hmm?
It'll be like a good thing.
Well, it'll exist.
Okay.
That's all I guarantee.
Okay.
Fair enough.
We should start studying any topics or something or practicing.
One sample, two sample t-test, one prop, two prop C.
Square.
Cut all this chi-squared stuff and then the end calculations.
Can I visit?
Yeah, you said.
We said one sample.
One sample, two sample t-test.
So what I do wrong. And I think by then.
Well, what you have to keep in mind is that p-values have to be between 0 and 1. So you're telling me that this is
This guy has a p value of
which
2.4.
tells me that it's way above. If you look at, and I'm not saying that what I've got is right. But if you look at what we have, this E negative stuff, that's kind of the important part here.
You know, they got 4.
So E negative 13
I'm thinking
means
so
0.0000000000002. Is that?
Oh. I just didn't get it.
Yeah. Yeah, so with the Excel, it does that. With Minitab, it only goes out to 3 decimal places, and it says the p-value is just 0.000. So. And basically what this is saying is there is an extremely significant difference between what we observed and what we expected. Going into it with absolutely no idea what's the correct answer is or what the theory is.
Thank you.
Right, you said one. Oh, sorry.
No, it's okay. You're
Yeah.
okay.
Yep, so one sample t-test, two sample t-test, one prop C, two prop C, chi-squared, and then calculating n. And the calculations we did that are on like the homework, what is the once you've done the t-test or the 2 sample t-test, what's the probability others will find a statistically significant difference? So that's all going to be part of the review on Tuesday. We'll go through and do a couple problems each because we will have time.
First homework. Is there like a specific chapter that it's?
No. No idea if I'm using the chapters.
Fair enough. The first page was mostly probability.
Yes. Yeah. This is my first time teaching this class with the textbook, and I'm already finding I don't like the textbook that we're using. And I don't. There's honestly only one stats textbook I've ever used that I thought was good. It was for my business stats class. but it's not the one that we have.
Fair.
So we cover everything that we're supposed to.
Mhm.
Just we're not necessarily gonna do it in the textbook.
That's fair. There's always
Yes.
more than one way.
Yeah.
Understand.
Yeah. It's like the first, like we're supposed to cover chapter, say chapter 6 or chapter 7 as our first chapter. Well, it's all the same. You use all that stuff in chapter 9. So why not do it in depth on 9? As opposed to this Karate Kid stuff. Wax on, wax off, wax.
Fair.
When are you gonna learn? When are you gonna teach me karate? Okay, wax on, wax. Oh, okay.
Thank you. Have a
So-
good weekend. Okay.
Just keep locking. No, have check in or just only.
That's it.
So I'm not sure about the expected values for that are up there, but that's about what you should get.
You're at 3.97 for E.
Well, I use the rounded values if you decimal values up to a certain place, that's gonna change things. I only do the expected value for one of these cells. You're supposed to do for all 4. So I don't know what the other 4 are, but
Okay.
so if you have something similar to like what I've got here, that's good enough. And I'm not, for right now, for what we're doing, I'm not gonna be too picky.
Okay.
Because if you, depending on what software you use, it's gonna do all, or potentially do all these things for you anyways. So this is more of an exercise just to get you used to using Excel and the formula and stuff, right?
I just had another question about the homework.
Mhm.
How do you how do you confirm the conclusion of these 3 moves? And then for you to do that.
Okay, so it's basically. So we've got. Essentially 2 different normal distributions. These are gonna have. Say the same read, blah, 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 blah. So. Same need. We're looking at. Does it confirm data? Does it confirm our results? That's. So if you have a value. And it's there, does it confirm the results? Yes. It's up here, does it confirm the results? Yes.
It's
If it's
outside.
out, if it's out here, no. If it's out here, no. For the conclusion. On this side, yes. On this side, no.
Okay. So it has to be greater than the margin of error.
Yeah, so. This is for results. And that's for the conclusion,
Okay, so even if it's here, it confirms the conclusion. Okay.
because our conclusion is, did we find a difference? Yes or no? As long as you find a value greater than the margin of error, the answer is yes.
Okay.
So this person here claims they found a difference. This person here claims they found a difference. These 2 people here are going to say no. This person confirms our data. This person confirms our data. These people don't.
Okay.
So part of this is when you look at scientific journals, when you're reading through whatever business articles, when you're reading the economic analysis, whatever, there's going to be some discussion in there, or there should be some discussion about how reproducible are the results. Well, what do you mean by the results? they don't really say much about that other. So I'm trying to break it down. So what's literally going to happen, or what happens in the real world? Like if you get into a psychology stuff, this person or performed the same experiment, and their data confirms what we believe,
Mhm.
but they're not going to conclude that there's a statistically significant difference.
Mhm.
So that's trying to wrap your head around. They confirm our data, but they said we're wrong.
Mhm.
Well, this is why.
Mhm. Okay.
Yeah, if it's greater than the margin of error, they have the same conclusion. Less than the margin of error. So out here, it's basically reject. Back here, it's failed to reject.
Mhm. Okay.
And then here, if it's between all of this, they confirm our results. Out here, they do not.
Okay. Mhm.
So, like if you're looking at data for does some training that you might have, or your place of work you want you to go through, does it actually help out with anything? Well, you might find that with one group of people, it improved their knowledge about whatever it is by this much on average.
Mhm.
We said it's say 10 units. Well, they said it's actually 14.
Mhm.
So, okay, fine. These people said it's say 7 units. All right. Well, if you've got 3 or like 5 to 15 here or something like that, they both basically show that the results we got are correct.
Mhm.
But this group is going to say, no, it's not worth it. This group here is going to say it's worth it. This group here is going to say it's worth it. Even though this group over here,
They didn't confirm our results.
right?
Okay.
So if you're confused, yes,
Mhm.
that is a valid response, because quite literally scientists don't know how to deal with this. I don't know how to deal with this other than to understand results are different from conclusions.
Okay. Mhm.
So,
Mhm.
yeah,
All right.
it happens. It's horrible, but it happens. Right?
All right. Thank you.
Yep.
So when I took DS301, we had like our tests, printed out and then did them at home and then took pictures and submitted them. Is that gonna be like this class or?
I haven't figured that part out yet.
Okay.
You're definitely going to be using a computer.
Yeah.
Whether or not you're going to be using a computer, say in here or at home, I don't know. But I definitely do not want pictures of the exam.
Okay.
I want the exam back.
Yeah.
All right. So more than likely, I'll pass out the exam on Tuesday. And then on Thursday, when we're scheduled to have the exam, everyone turns it in and we start talking about the next topic.
Okay.
So to have like 2 or 3 days, should have like 2 days to work on it. All
Okay.
right.
Is it gonna be like, cause we had like multiple choice and we had like handwritten,
I hate multiple
Okay.
choice.
so it'll be like all handwritten problems.
Yeah, it'll
Okay.
be basically like what we're doing in here.
Okay.
So there'll be questions, you do a calculation, then questions where you interpret the results.
Okay.
And you give your opinion about things.
Thank you.
All right. Yep. What'd you do this time?
I had 2 questions, but I think while you were explaining that other stuff, I think I figured it out. We broke our calculators mid lesson and I think it's I don't know how to go. But it looks close, but it's not what you got. Because
So
it's 86.62. That one's okay.
Yeah.
Now it's way different.
And that's.
9.8, and then 82, 68, 1, 98, and 62.
Number from the speech, the 30. Okay.
Never mind.
Oh, what are you seeing for your swear there? So double click on that. So.
Yeah.
So what you've got here is fine, because all these values are over. Of 10. What you're trying to do here is totally fine, not gonna be that big deal. But. The way. That. This is, the way that my calculator is doing it. It's more like that. So.
Do you want the, p-value and the chi-square?
P-value is kind of like the most important part. What I wanted was what you get for A, B, C, D, and E, and then the p-value.
So you wouldn't say the exam looks like the homework. It looks like what we're doing in class, but we're taking it home, the exam.
Most likely. And then you have to hope that you remembered how to create all those Excel sheets.
We're not gonna be able to,
I say mine.
yeah. So we're not able to use our saved Excel templates for main class.
Yeah. Yeah. Yeah, just hope that you have those done correctly.
I saved it to OneDrive.
I don't trust like
Bro, the
the
OneDrive?
desktop.
Oh, really?
Yeah, because the first like big project I had, my first stats class here, I sent it using OneDrive and a file clone.